Hi, welcome to Kinetics Part 4. My name is Dr. English. Today we're going to be talking about representing energy in chemical reactions. Specifically, we're going to be looking at writing exothermic chemical reactions, an exothermic reaction example, writing endothermic chemical reactions, looking at an endothermic reaction example, and finally a little bit of practice at the end. So let's talk about writing exothermic chemical reactions. One of the reference tables that you need to be able to look at is reference table I, which is heat of reaction at 101.3 kPa and 298 K, which is roughly room temperature. So let's look at an example that it can be found on table I, and that is nitrogen reacting with hydrogen to give you ammonia. Table I lists this reaction's H as negative 91.8 kilojoules. Since the value is negative, the reaction is exothermic. And if you're looking at your reference table right now and you look at the very bottom, you'll see that there's a little asterisk and it says the values that are negative are exothermic. So that's something to keep in mind. The reaction is written with the heat/energy appearing on the product side or the right side of the reaction. So if you want to represent heat as an exothermic reaction, you want to list it as a product, which is why we would write it over on this side over here. Now remember, we don't have negative signs in chemical equations. So even though there's a plus sign right here, because it's on the product side and we look at this as a forward reaction, energy in this case is being released, therefore it is exothermic. Let's look at this chemical reaction from another perspective. This reaction produces 91.8 kilojoules of energy released for every 2 moles of ammonia produced. How much energy would be produced for 1 mole of ammonia? Now you might be saying, what do you mean 2 moles of ammonia? If we go up to our balanced equation right here, this is saying that for every 1 mole of nitrogen plus 3 moles of hydrogen that produces 2 moles of ammonia, 91.8 kilojoules of energy will be released. So this question is asking, well, what if I want to figure out what it's going to be for just 1 mole of ammonia? So I'd say 1 mole of ammonia, NH3, and I'm going to know that the ratio here is for every 2 moles of ammonia, I'm going to release 91.8 kilojoules. And since it's released, I could have put a negative sign in front. So if I divide 91.8 by 2, I find that is 45.9 kilojoules. So the answer here is 45.9 kilojoules per 1 mole. Now let's use table I to figure out how we'd write the equation for the heat of formation of aluminum oxide. The first thing that we need to look at is the formula for aluminum oxide. We know that aluminum has 1 oxidation state associated with it with Al plus 3, and oxygen is O minus 2. So we're going to go old school here, and we're going to do the crisscross method, and we're going to bring the 2 down here and the 3 over here. So our formula for aluminum oxide is Al2O3. Then we're going to look at the delta H value of aluminum oxide on table I. And if we do that, we find out that aluminum oxide is negative 3,351 kilojoules. Now it says how much energy will be released for 1 mole of aluminum oxide. Before we go to that, we should write the balanced equation for the formation of aluminum oxide. And since this is a negative sign right here, again, that value is going to appear on the product side. Let's go ahead and write the chemical equation, including the delta H value that's listed up here. So we're going to have aluminum plus oxygen is going to give us aluminum oxide, which we figured out the formula is up here. So that is Al2O3. Now I could automatically balance my aluminum, but I really should pay attention to my oxygens here, because on the reactant side I have 2 moles of oxygen atoms, and on the product side I have 3 moles of oxygen, and I need a common number for each of those. And if you say, oh, the common number is 6, you're right. So if I have 3 here, I need a 2 in front of here, because 2 times 3 gives me 6. And then I'll need a 3 over here, and 3 times 2 gives me 6. So that's the oxygens are balanced. And then I go back over to the product side. 2 times 2 gives me 4 aluminum. So I'm going to need 4 over here, which means that this delta H value for aluminum oxide really corresponds to 2 moles of aluminum oxide in my chemical equation. Therefore, I'm going to list this, because it's an exothermic value, on the product side. So 3,351 kilojoules. Now we go back to the question of how much energy would be released for 1 mole of aluminum oxide. Well, if this is for 2 moles of aluminum oxide, what I need to do here is say 3,351 kilojoules divided by 2 moles. And if I work that out, I get 1,675.5 kilojoules. So rewrite that again over here, 1,675.5 kilojoules of energy released per every 1 mole of aluminum oxide. Now let's talk about writing endothermic chemical reactions. So again, we're going to use reference table I, and here's an example that's off the table. 2 moles of carbon plus hydrogen gas gives me C2H2, which is known as ethine. Table I lists this reaction's delta H as positive 227.4 kilojoules. Since the delta H value is positive, the reaction is endothermic. The reaction is written with the heat/energy appearing on the reactant side, or the left side of the reaction. So if I was to rewrite this, including the energy, I'd be putting my heat over on reactant side, because it's an endothermic reaction. So let's look at another example that's off of table I. Using table I, how would you write the equation for the heat of solvation, not salvation, solvation of ammonium nitrate? And solvation is just the process of dissolving something in water. So the formula for ammonium nitrate, now you should depend on table E for this formula. So ammonium is NH4 plus 1, nitrate is NO3 minus 1. So the plus 1 and the minus 1 are going to cancel each other out. So when I rewrite this formula, I'm going to write NH4NO3. The delta H value for ammonium nitrate on table I is 25.69 kilojoules. So the chemical equation, including the delta H value, would be NH4NO3 plus 25.69 kilojoules produces NH4 plus 1, aqueous technically because we're dissolving it in water, plus NO3 minus 1, aqueous. And we should probably mention that we are starting out with a solid over here. So a certain amount of energy is absorbed to break up this compound into ions to form the ions in solution. Therefore, it's going to absorb energy from the surroundings and bring it into the system, so the surroundings themselves will experience a decrease in temperature, which is why it will appear cooler. How much energy would need to be absorbed to dissolve 2 moles of ammonium nitrate? In order to dissolve 2 moles of ammonium nitrate, what we would do is we would take 2 moles and we'd say we're going to multiply that times 25.69 kilojoules. And when we do that, we find the answer to be 51.38 kilojoules. So we're just multiplying the number of moles times the molar value, which is listed on table I, for ammonium nitrate. So the answer here again is 51.38 kilojoules. Now what I'd like you to do is stop, read over the 2 questions that are listed here, and see how you do. Welcome back. For which compound is the process of dissolving in water exothermic? And again, you're going to need to use table I to answer this problem. So what you should have done is looked up the different values for each one of these and figured out what that value is. And if you picked sodium nitrate as the right answer, you were correct, because sodium nitrate has a negative delta H value, while NaCl, NH4Cl, and NH4NO3 all have positive values. Let's look at the next question. Given the balanced equation representing a reaction at 101.3 kPa and 298 K, and here's our reaction, which of course we've already seen, we're very familiar with this. Which statement is true about this reaction? It's exothermic and the delta H equals negative 91.8 kilojoules. It's exothermic and delta H equals positive 91.8 kilojoules. It's endothermic and the delta H is negative 91.8. It's endothermic and the delta H equals positive 91.8. All right. Well, we see that the energy is listed as a product. And if the energy is listed as a product, it has to be exothermic, which means C and D are out. So both of these say exothermic. Now we're going to talk about the delta H's. We know that if a reaction is exothermic, then the delta H for that is going to be negative. So if you chose A for the correct value there, you're right. It's exothermic, and the delta H is going to be a negative 91.8 kilojoules. So what did you learn in this tutorial? We talked about writing exothermic chemical reactions, and we looked at an exothermic reaction example. We talked about writing endothermic chemical reactions, and then we looked at an endothermic reaction example, and finally we did a little bit of practice at the end. Need more help? Feel free to contact me. Have a great day.